Hello, Mr. Sorrentino here, presenting another one of these videos for our Math 31 lecture series, and this is dealing with section 4.1, polynomial functions and models. In chapter 4, we're going to explore a lot of solving polynomial equations, mainly focused around finding the zeros of polynomial functions. Because ultimately, finding those zeros is what I would essentially do to solve the equation. Because finding a zero for a function it could be the same thing, because all I need to do is take any equation and set it equal to any polynomial equation, set it equal to zero, and that will allow me, to go through procedures to find the zeros at that point, much like we did in several things with quadratic functions. And we have already studied a few polynomial functions. Linear functions are polynomial functions. Quadratic functions are polynomial functions. It's just that now when we start dealing with quote unquote polynomial functions, we're going to start seeing powers of x that are more than 2. So, and as I had mentioned before, when we talk about graphs of anything, sometimes, when you're trying to graph things using the methods we started this course with, namely naming some numbers and just putting into the function and seeing what you get and plotting those points, you can miss a lot of different things about a graph. So so we had graph transformation techniques. That's why we had specific procedures for quadratic functions and linear functions. With polynomial functions, we're going to study different aspects of them, so you kind of know what to expect, what you're looking for, so that you know if you're plotting points. And you picked some x's and solved for y's, if you have enough to really go by anything. Also, these methods will also help us get pretty decent graphs of them by simply picking the right points along the way so that we can figure out what it really does look like and maybe sketch a graph of them. This also helps dealing with the calculator as well, because of the fact that some people will use the calculator to get an idea of what the function looks like, but they may not have their windows set up to see enough of it, and they start making conclusions based off of only seeing part of the graph, and that's where sometimes other errors could present themselves. So when we go over these characteristics over this and the next, I think the next lesson as well, this will help us determine various aspects of these polynomial functions, so that when we're starting to determine solutions and other things from it, that we are using an entire graph of the function to make our determinations. And so in your notes, you see that they do have what a polynomial function is. And basically, it's basically a function written in multiple powers of x, where you have, coefficients that are real numbers. Now, real numbers versus specific types of real numbers like integers and rationals and things like that, they'll help you determine other characteristics we'll talk about later. But the main thing that we want to keep in mind is that we're talking about instances now that, our powers are all integer powers and they're all positive. So we're not going to have any negative exponents, although towards the end of this we'll start talking about rational functions again. We solve some rational equations, but some of those we're talking about rational functions. We're not going to deal with any powers that are fractions where roots would be involved. So, these are very specific. And as we go through this, we also want to know like what a polynomial function looks like as far as a graph goes, so we know if we're dealing with one or not. So one of the first aspects that's mentioned here is a polynomial graph is a smooth, continuous graph. It has no breaks, no holes, no sharp corners. So, I'm not going to see those features on a polynomial graph. And I shouldn't see them if you're sketching a picture of one either. Another thing we discuss is what the end behavior looks like. This is very useful for determining whether or not you have a full picture of the polynomial function. And as we go into um, determining later, if we're seeing a complete picture of the function, or if we've produced a complete picture of the function, the end behavior does help with that to a certain degree. So As we talk about this, and I don't have it emphasized here, but it is something that's been brought up in other courses and things, that we do mention the degree of a polynomial. The degree of a polynomial, and I should say polynomial function. The degree of a polynomial function is the same thing as basically saying the highest power of, and I'm going to put in quotations, x. Whatever the variable is. We use x most often, so I'm just going to put x there. But if we had a function in terms of some other letter of the alphabet, like r or something, it'd be the highest power of r. That's the degree of the polynomial. That degree tells us information. First, it tells us how many zeros we could possibly expect, and the zero of a polynomial is very much like the zero of a quadratic, or they're also known as other textbooks as roots. A zero of a polynomial is something that makes the polynomial function equal 0. So basically, where it crosses the x-axis, and so basically, when we're talking about the degree of a polynomial, that first could tell us possibilities about how many zeros I could expect. It also gives us an idea about the shape of the ends of the function. See, and that's what these little markings here are indicating. It means there's a whole bunch of different stuff that could be going on in between, in the middle of the function, but if I have an even degree, that means like your degree is either 2, 4, 6, 8, so forth and so on, then I know my graph is going to end pointing in the same direction. So here they're both up, here they're both down. So an end behavior for an even degree polynomial is going to be, both ends pointing in the same directions. It's up if the leading coefficient is positive, and down if the leading coefficient is negative. Leading coefficient, very misleading as far as the word goes. That's the constant multiplied to highest power of x. Again, put that in quotation marks because it could be other variables as well. It's important to note it that way. Now, when we write polynomials in standard form, the standard form of a polynomial is typically written from highest power to lowest power, and that's where the word leading comes from, because this would be the leading coefficient. It's on the highest power of x that you have in your polynomial. Now, some of the functions you might be encountering may not be written in standard format, so you have to be able to recognize what the leading coefficient is. And of course, getting back to the end behaviors, if the degree of the polynomial is odd, then basically the two ends are going to point in opposite directions. And for instances where the leading coefficient is positive, it's going to be pointing down on the left and up on the right. And then that's going to be reversed if your leading coefficient is negative. So there's a lot of things that go on with this that you have to be aware of in order for you to know what the end behavior looks like. And therefore, but it's important because if you're looking at a graph of it on a calculator, try to get some idea of what it looks like, or you've plotted it yourself by plugging some random points in. If you're not seeing the ends look like, what they're supposed to be, that might indicate that you have more points that you need to try out, or you need to expand the window on your calculator to see more of the graph, so that you are looking at it in its entirety. So for the first example you're given, you're just simply asked to describe the end behavior, and that's by drawing that little picture of these two functions. Now, for this one here, when I look at the f of x for a, it is written in standard form, and this is a degree 4, which is even. That means that the two ends should be pointing in the same direction. Now, are they going to both be up, or are they going to both be down? So right now, knowing it's an even, I know it's either going to be this or it's going to be this. As far as the end behavior goes. Now, which one is it? Well, the leading coefficient's a -3, which means it's the leading coefficient's negative. So if it's negative, that means that the two ends are pointing down. So that means that this one here is not the right answer. It's that one. So I would expect the two ends to be pointing down. So if I were to make a graph and I don't see any indication that the two ends are pointing in the downward direction, basically where the graph goes on forever and ever, then I'm not looking at enough of the graph, and there might be other things going on that I need to be aware of. Whereas this next one, this is not written in standard form. As a matter of fact, the x's are increasing in value as I move along. So this is a degree 5, which means it either is going to look like this, or it's going to look like this, as far as the end behaviors go. I got to figure out which one it is. I'll have a lot of students that'll make the correct assumption that it is a degree 5, but then they'll tell me that the leading coefficient is 9. It isn't. The leading coefficient is 3, which is positive. And from the rules we just learned about, if it's a positive, leading coefficient, then it should start off at the left-hand side pointing down, and at the right-hand side be pointing up. So the first one I drew for this one is the correct answer. The second one's not. So that's not the correct. So those are the correct end behaviors for this. Not a major thing so far, but it is important. You're going to see its importance hopefully as we progress through these things. The next thing you're given some information about is the special names of some polynomials, because you're going to see at times they're going to say stuff about it being a quadratic polynomial or a quartic. You may see those words come up. It's important to know those particular names. Notice that the function y equals 8, which would be like f of x equals 8, a constant polynomial, it's a degree 0. So that is a polynomial function. We talked about linears already. We talked about quadratics in the previous chapter. We have cubics, that's a special name. Quartic is a special name. Quintic is a special name. And you may even see these names being used occasionally in some of the problems you might be given. Usually after degree 5 for this textbook, they just simply say it's a degree 6, degree 7, degree 8. I've seen other textbooks called degree 6, basically sexic, which, doesn't sound that great. Degree 7, it would be septic, which is even worse. Octic, nonic, and then after you get to degree 9, you start getting into some of the other, like, they don't really sound really good for naming them, so they tend to fall off and just resort to just stating the degree after that. Now, we talked about zeros of quadratics before. We want to find the zeros of a polynomial function. It's the same thing. It's basically, when I asked the question in example 2, are these zeros of the polynomial function? What I'm asked to do is determine if these values of x make f of x equal to 0. So when I'm looking for zeros so don't just think it's the number 0 all the time. I've seen students make that mistake. The zero of a given polynomial, if I can get the right thing, the zero of a given polynomial means I'm looking for x's such that f of x equals 0. So that's what I'll be doing in each one of these instances. I'm going to substitute the number in for the x's into the function and see what it produces. So for the first one, again, my recommendation is make sure you put when you show your substitution, so I know that you're substituting correctly, and use those parentheses as your substitution, because that should help you with the order of operations and what needs to be done first. I would take care of the exponents first in this. So, -1 cubed is -1, so the first term is going to be -2. -1 squared is 1. -3 times that is going to be a -3. -1 is just going to be, adding a -1 is going to be the same thing as subtracting 1, and I have a +6. And so I have negative 2 minus 3 minus 1 plus 6. That does come out to be 0. So the first one, x equaling negative 1, is in fact a 0. When I go to the second one, f of 2, did my substitutions first. I'm now going to start working these out. 2 to the third power is 8 times 2 is 16. 2 squared is 4 times 3 is 12, and I'm subtracting that 12. Plus 2 plus 6. 16 minus 12 is 4, plus 2 is 6, plus 6 is 12. That's not equal to 0, so, this is not a 0 of the polynomial. And of course the last one, I would do f of 3. So here I have 3 cubed is 27 times 2 is 54. Minus, 3 squared is 9 times negative 3 is a minus 27. Plus 3 plus 6. 54 minus 27 is 27. Plus 3 would be 20. By 30 plus 6 would be 36. So this is also not a 0. So determining whether or not things are zeros of a polynomial are fairly easy. I do show you here briefly. I'm not going to necessarily pull the calculator out to show this portion of it. However, to remind you that you could find zeros of the polynomials just by using the procedure we used before of evaluating numeric values of functions. We've done that in previous lessons, so I'm not going to go through the whole process of doing that again. Hopefully it's something you're more familiar with and have used enough at this point to know how to do it. Now where I am going to use the graphing calculator is when we talk about zeros of polynomials, or sometimes they're known as roots as well. Sometimes when you're dealing with polynomial functions, especially with them, you may have situations where that 0 may, because remember what I said before, the degree of the polynomial will often tell me that I have a certain number of zeros that I could expect in the function. And what that means is that, like for this one here, example 2, I would expect that there's 3 zeros for this polynomial function. I've only found one. I found that, a negative 1 was a 0. And I could use that piece of information, and we'll go into how, as we move through this particular chapter, I could use that information to determine what the other zeros are at that point. So, so if I could find one of the zeros, either by trial and error or just putting values in it and determining that one of them makes a 0, I can sometimes find the other ones a little bit quicker because I might be able to factor it out and use quadratic or linear techniques to find the rest. But at the same token, there are instances where I may have a 0 that actually counts as 2, 3, 4 different zeros for that polynomial function. How am I going to know that when I see it? And that's what we got into talking about multiplicity. So multiplicity is an instance where I have zeros that count as being more than one 0. So for instance, I have this function here, f of x equals x plus 4 cubed times x minus 2 squared times x minus 5. If I would go through and FOIL this out, I would have, or do all this distribution, it might take a little bit of time, I would have a 6th degree polynomial. I'm just going to note that here. I'm not going to show that because I actually have a picture of the graph right in front of us just for our knowledge and having it, because I'm more interested in where it's passing through the x-axis. But this is a 6th degree polynomial. Now it stands to reason for this to equal 0, either this quantity has to be 0, this quantity has to be 0, or this quantity has to be 0. That's why I left it factored so you could easily see what those should be, because negative 4 would make x plus 4 0, and if I cube 0, it's 0, and then the whole rest of it becomes 0. 2 would make the x minus 2 in the middle become 0. And again, if I square that 0, it's still 0, and the multiplication with the other two quantities would still be 0. And of course, 5 is a 0 because it makes the third quantity 0. So these are the zeros of the polynomial. The fact of the matter is, those are the only zeros, because those are the only values of x that would actually make this polynomial function be 0. But you might be saying, well, that's only 3, and this is a 6-degree polynomial. Where did the other 3 go? Well, that's because since this was a result of cubing the x plus 4, this 4 here, notice, that's what the negative 4 is right here. Notice I have this graph kind of flattening out. It passes through the point, but it kind of flattens out. That's an indicator that I have an odd multiplicity, and it's more than 1. If it's 1, like for the 5, so this is the x equals negative 4, this is the x equals 5, it just passes through. It doesn't kind of level off and flatten before it goes through. It just goes through. So negative 4 has the multiplicity of 3, which means it counts as 3 zeros. That's what we mean by multiplicity. X equals 5, as we mentioned, has a multiplicity as 1, which means it counts as 1 zero. Obviously, because of the squaring on the quantity of x minus 2, that means that there's actually two quantities of x minus 2 involved in this function, which means those two quantities are where the x equals 2 is going to make this 0. That's why it has a multiplicity of 2, which means it counts as 2 zeros. I can typically tell an even multiplicity if it's an instance where the graph is what they call tangent to the x-axis at that point. That means it's going to become 0, but it doesn't pass through. It turns around there and goes in the other direction, so it doesn't really pass through the x-axis. It does touch the x-axis, but doesn't pass through. That would also hold true if it had a multiplicity of 4, multiplicity of 6. The only thing you would see differently is you would see it also flatten, but it still wouldn't pass through. The multiplicities that you're going to be responsible for in this course are typically going to be instances where you have multiplicities of 1, 2, or 3. And the graph will help you figure that out. You're not going to have to worry about multiplicities of 4 or 5 or 6, but technically you could figure out what they are along the way. But figuring out these multiplicities becomes important as we get into more polynomial equation solving later. So these multiplicities, that's how you determine them. It's based off of what I see graphing. And that's why we use the calculator at times to assist us in the graphing so that we could try to figure out some things about it and find any zeros that, may or may not exist. Because one of the things you'll be asked to do with polynomial functions is you may be asked to find any zeros that are non-real. And some of them will have that. And you'll be able to determine if you have non-real zeros that just won't show up on the graph, or if you have zeros that are actually on the graph, but some of them should be counted more than once. So, moving on to the conclusions, which I kind of already gave for this, and I'll let you kind of have a chance to answer them before I fill them in. If C is a zero of a polynomial and C has the multiplication of k, multiplicity of k, I should say, then if k is odd, then the graph blank, and if k is even, then the graph blank. So answer these questions to the best of your ability, and we'll go through them in a moment. Okay, if k is odd, then the graph passes through the x-axis. So if it's an odd multiplicity, including 1, which is the most common one you're going to see, it passes through at that value. So if I say that if 4 is a 0 of the polynomial, I should see the graph pass through x equaling 4 on the x-axis, and it passes right through. Now, I had to judge if it's just going straight through, or if it's leveling off as it passes through and then gets steep again. That'll let me know if it's a multiplicity of 1 versus a multiplicity of 3. If k is even, then the graph is tangent to the x-axis. And both of these I should really say at c, because that's what we're assuming is the value of the 0. And tangent, again, simply means touch but not pass through. So that's how you can determine the multiplicity and determine whether or not a particular 0 may count more than once. So for the next example, which is more of an application, because we don't get more into any more of the details of polynomial functions in this particular lesson, basically how to interpret some things. Circulation of daily newspapers. In 1985, the circulation of daily newspapers reached its highest level. The quartic function, so again, they're throwing out a word here, which simply means a degree 4 polynomial, which I can clearly see in the polynomial function they give us, represents the number of newspapers in thousands that are sold daily, where X is the number of years since 1940. Very important. That means if I'm given a date, I need to take away 1940 from it to get the value of X I actually use for the formula. Using this function, estimate the circulation of daily newspapers in 1945, 1985, and 2008. So you see here you are given what 1945 equates to. That means X equals 5. What 1985 equates to, which is X equals 45. And you're also given the fact, and this won't necessarily be the case in your problems you may be given on a test or a quiz, 2008 correlates with X equaling 68. You're used this to estimate the circulation of the daily newspapers in those years. So I want you to take a moment and make your calculations. Try to round, I would say round to the nearest thousand for our cases, so that, for when you answer them, I can have a consistent answer as far as being what the right answer is. And then we'll go through these. Well, the calculations could be a little bit daunting on this one. So, and that's why I showed a calculator at the bottom of it, of the page. I'm gonna demonstrate the calculator again, just kind of reacquaint you with how to use the functions on this. And so I'm going to bring up my calculator and the detached LCD, and I'm going to put that function in here. And I'm going to probably do a fast motion on this so that you can see it entered in here once it's all done. But this may take a little bit of time. So here we go. So now I have the entire function in there. Now to talk about a couple of things, maybe I want to know what the graph looks like. And as I look at this, I notice that in my function up here, the x didn't seem to appear. So I do want to insert that here. It's the x to the fourth, not the number to the fourth. I just want to make sure to go through and make sure everything's cool with what's supposed to be here versus what's actually showing up on the calculator. There we go. Sometimes typing fast on any calculator can cause an issue. I might want to see what it looks like to get an idea of where these things will be and things like that. But I also want to do this to demonstrate, how knowing some things about end behavior or whatnot could help with this. So Let me graph it the way it is now, and chances are I may not see much of it because this is something we set up in a previous graph. This usually means up here it's working. As long as I see that, it means it's being drawn. But right now I'm really not seeing anything. And that's because of the fact that, I have values here that are going to be in play that I may not be able to see. I mean, heck, I have X values that go to 68 for this. I don't know how high up. I mean, this is going to be in thousands in the long run. And the fact of the matter is, you know, with the constant term itself being 41,334, which means that's 41,334 thousands. So you're talking about having, thousand thousands, which is a million. So that's 41, million 334,729 approximately. Um, you need some rather big numbers on the Y's. So uh, I'm going to adjust my window accordingly to make it fit better, maybe. I know I want to go from maybe have something over here like, in the negative so I can see my axis. But maybe I'd like to go to 70 to see what goes on with my X values. I don't necessarily want to go by ones because this is going to, make my axis look kind of yucky. I'll go by tens. My Y min, I might want to go maybe, like, let's say maybe negative 1,000. But maybe for the sake of argument for this one, just let my Y max be maybe 50,000. Might want to see more of it later. And I just go by thousands. See if that does any good. I don't really mess with the resolution. These two things, I mean, the delta X can sometimes, if the smaller that number is, the slower the graph can be drawn. You can mess with that a little bit if you want the graph to graph faster. I don't really care for that. I'm just going to graph this now and see what it looks like now. And as you can see, I mean, I see parts of the graph here. And the question is, was that a good enough part of the graph? Well, I know that I'm missing some stuff up here. It is pointing on the left-hand side down, and it seems like it's pointing down on the right-hand side, which means we have a good range of X values here. Because the end behavior tells me, since it's an even degree polynomial, they should be pointing in the same direction. And since this is negative, it's pointing down. So I have enough of X coordinates here, but there might be some other thing going on up here that we haven't talked about how to find those yet. So I might want to make my window go a bit further. Maybe make this 100,000. And maybe make this go by 10,000 instead. As I said, if you know some of the features about graphing, you might be able to figure out, if you're seeing a good enough picture or not. And it seems as though that even though it's quartic, and sometimes in the middle, I could expect to see possible more fluctuations I see here. This looks almost very parabolic, and that's pretty good. That means it's a decent function. I could also now trace to figure out what these things are if I needed to. So having that in there lets me look at some graph behavior. And I can also see here, it looks like, when my X values, which are going by tens down here, when X is about, 40, it seems as though that's when I'm going to reach about a maximum as far as the circulation goes. So as I look at this, when X is 5 in 1945, I expected it to be a certain value over that initial 41,000. In 1985, which is 45 years later, I would expect it to be kind of where its maximum is. And so I should see a higher value for its readership. And then in 2008, I should see it be down a bit more because it should be somewhere around here. So that also lets me kind of anticipate what the answers may be and how they should look when compared to each other. So as far as evaluating them go, especially when you have a lot of nasty decimals in here, if you have some really like nice integers or some doable fractions like 1/2 and things like that, then by all means you should try to do it by hand first and then use the calculator to maybe check. For ones that you have nasty decimals like this, I'm going to say you should really use the calculator to help you. And the biggest part was typing it in, because now all I need to really do is just go to variables, go under Y variables, and choose Y1, because that's where I type that formula in. And so if I want to see what happens when x equals 5, I'm just going to put in parentheses 5, and that's the readership. Now remember, this is in thousands, so that's 48,277,000. So I would say it's about 48,277,000 readers for the newspaper, if you round it off to the nearest, nearest whole. For 1985, scooch this over a little bit, bring these guys back up. If I hit second and enter again, it brings back the last thing I entered in. So I don't have to worry about going through the entire menu to get that Y1 back. I just to change that to a 45. So in 1985, when X is 45, that readership is 61,897 thousand readers, or 61,897,000 readers for this circulation of this newspaper. And then lastly, when I look at this x equaling 68, which I see is over here, which is what corresponds to 2008, again, I can just replace this with a 68. And as I mentioned, I expected to go back down again. It did, which means this would be 48,836,000 readers approximately, with this newspaper at that time. So that's how your calculator could help you with that, and how some of the graphing techniques can help you figure out what's going on with it and know what to expect for right answers and so forth. And that brings me to the end of this first video. In the next video, we're going to start going over some more features of polynomial functions to help us graph them even more accurately and know what they should look like. And find zeros for them and so forth. So if you have any additional questions on this video, please make sure to bring them up in class, come to office hours or so forth. Until I see you then, or until the next video, I'll see you around, and have a good day.